Okay, yeah, hello everyone. I think I'm live. So my name is Anthony Alaribe, and I'm the CTO of a company called Monoscope, a software monitoring company. So today I want to tell a story. So it's a story about building a monitoring platform, a massive storage bill, and why we ended up doing the one thing everyone tells you not to do. We built our own database. So we call it Timefusion, and it's built on some incredible open source projects, primarily the Apache Datafusion and Delta Lake projects. So just for some background, yeah. So my team and I built a software monitoring platform called Monoscope. You can think of it as something like Datadog or Grafana. So our customers basically send us all their logs, metrics, traces, and we ingest all of this data, store it, analyze it, and then users are able to leverage this data to build dashboards, to create alerts, and to figure out why their systems are on fire. As you can imagine, this is a time series problem, and it's a massive, write-heavy, high volume data problem. And like any good story, it started with trouble. So when we started, we did the smart practical thing. We didn't reinvent the wheel. So we choose the timescale DB database, which is it's basically a fantastic extension on top of Postgres, purpose built for time series data. And then to move even faster, we use the timescale DB cloud. Okay, so it was perfect. It worked. This is the timescale logo, by the way. So it worked and it scaled, so we could focus on our application um, just for a couple months. So we're a bootstrapped startup, and we had these very unsustainable bills because not long after we started, we're getting these $2,000 a month invoices just for storage. And this was 3 years ago when we had a tiny fraction of the customers we have today. So we were a bootstrap startup and our entire bank account could feel this. We couldn't build a business on this kind of cost structure. Yeah, and at the time, even the database bill alone was exceeding the entire revenue we were making as a business. So, of course, we're forced to change something. So, the plan B change we went on was to, instead of using the Timescale DB cloud, to self host it on our own infrastructure. So this solved the immediate cost problem. So our bill went like way down. But then it traded one problem for another, a much scarier problem, which I like to call the storage trap from these platforms. So the thing is this, when you self-host a database like Postgres, you have to decide your basically your cluster and your disk sizes upfront. So how much storage would the servers that you buy hold? And especially because we were really trying to save costs, we're also on these bare metal servers, which where you have to pre-provision and lock into a 1 year or even 2 years contract just to bring down costs. So this was okay. We selected a lot of terabytes of storage for our cluster, and we felt we're set and ready for the next phase. Then we signed a new customer, a fairly good customer. This customer started sending roughly hundreds of gigabytes per day. We did the paper napkin math, and we had a few months maximum before our servers would run out of storage. So what do you do in such a situation? Well, you don't have a choice. You have to upgrade or risk running out of storage and disappointing all of your customers. So, we got a new server with even more storage. Um, Now we moved to even more terabytes of storage capacity. We tried to over provision just so that the same issue doesn't happen too quickly. And if you've ever done a Postgres database migration, especially with something like Timescale DB, it's very stressful. All of the PG dumps and PG restores, and setting up complex data replication. And here's the killer issue. So we're an observability platform. So we have one job, and that job is to write data, right? To ingest logs and traces and all of that. Now, the problem with migrations is that during a migration, you're not supposed to write. Even if you're trying to have a zero downtime migration, you have to pause write at some point. So that meant there was no choice. Our customers were going to come into their dashboard and for some time see empty, seat empty. And this is something you don't want this, right? Because you can lose trust from your customers when this happens. But eventually, we did this since we had no choice, and the migration was successful. We got a much bigger server with like so much more storage to buy ourselves time. It was expensive, and brought us back to the original problem of paying even more for storage than what we needed at the moment. Um, so we're right back to, like I said, paying for storage that we're not using, just to avoid another high risk migration. And sure enough, a couple more big customers came in, and just a few months later, we had risk of running out of storage again. So something had to change, right? The core problem was this. With a traditional database, storage and compute are tightly coupled. So you're stuck with having disk and the disk has to be on the server where the compute is happening. And that's how, for example, Postgres runs traditionally and pretty much every database runs. But what we needed was something that a lot of cloud platforms already have, which is object storage, something like S3 or R2 or whatever. Basically, we wanted to separate compute from the storage. That way, we can have a fixed amount of compute servers, but then the actual data storage can be, for example, in object storage where we can get unlimited data scale, and the servers themselves were not what would limit how much we can store. So we wanted to pay for exactly what we used and scale as far as possible. Now, the funny thing is this, Timescale DB has this feature. But you only get this feature if you're using their cloud. And that is the exact BO that we ran away from in the beginning. So we had to go shopping, looking at the other options on the market, for example, ClickHouse, and same story. So open source ClickHouse forces you to store all of your data also on one server, but the ClickHouse cloud is actually implemented in such a way that data is stored in object storage. So that feature is not available to the open source users, or if it's available, it's usually like some form of hot and cold storage, not proper primary storage in object store. So we looked at other platforms like Apache Doris, Starrocks. There's all of them. It's always the same problem. Any option that lets you use cloud storage was either super expensive, so it's tied in an enterprise deal, or it was not open source. So at this point, it felt like we were literally being forced to build our own database just to get compute storage separation and object storage support, especially without going bankrupt. So I remember tweeting about this. The responses were anonymous, anonymous. My English is going away. So everyone was basically saying, "Don't try, don't do it. You're gonna regret this." And they were not wrong. Building a database is famously complex, but we were completely out of options. We were a growing business, and our core infrastructure was fundamentally broken. And also, we're a business in a market where we couldn't charge a crazy amount, so we just don't have enough money to pay for crazy amounts for storage. So we're going to build a new storage, a new database, but we didn't want to reinvent the entire wheel, right? We wanted to pick our battles and focus on exactly what we had to do. And what we did was basically leverage some building blocks from the ecosystem, specifically the data fusion projects, the packet file formats, and everything is just built in the Rust ecosystem. Just we didn't want to fight performance problems that we could escape. So the first block we used was this Apache packet file format. Now, if you've used CSV, that can be a way of thinking about this. It's basically a file format like CSV. The main difference is that CSV makes you think in one row at a time, while Parquet makes you think in one column at a time. And this is a superpower because if you're doing anything analytics or telemetry, most queries that users or would run, or most questions users would try to answer, would be things like what is the average CPU usage over the last 3 days, you know, and that is just one column, CPU usage column. So columnar formats like Parquet helps you get an entire column super cheaply without having to pull out every single other unrelated data, and that adds up to the strengths. So if you look at the screenshot, for example, you would see this is how you would store something in Postgres or in CSV, but in Parquet, it's one column at a time. I mean, there's some downsides. For example, it's an immutable file format, but we don't need to stress about that for this talk. The next project that we leveraged was the datafusion project. Now, the datafusion is, I like to think of it as LLVM for database. If you know LLVM, you know it's these targets that a lot of programming languages build to. And then, like for example, Rust compiles to LLVM, and then LLVM now gets compiled to object storage. And a lot of languages do the same. So many different languages share an LLVM core somewhere. So data fusion is similar in the sense that it focuses on the optimization of queries. So you give it a query, it thinks hard about how it could be rewritten and restructured, so it can be executed, pretty cheaply. And then you can now figure out, how are you going to um, um, execute the query plan that data fusion gives to you at the end. So a little picture of what that looks like. So you can have your data, and you can have like the different actions you want to do. But the main thing data fusion is doing for you is that you give it a query, for example, SQL, it creates a logical plan of how that SQL would map to whatever data you want to query, and then it optimizes it and eventually gives you an execution plan. And you now take this execution plan and figure out how you want to, actually, I don't know, what code are you writing to turn that execution plan into the results. So it does the whole passing of SQL, and does a lot of steps that are quite difficult, but it's nice if someone else can do it for for us. The third building block for us was the Delta project. When you build this kind of data stores, you always have to think about how do I structure the data so that when I'm running a query, I can ignore as many files as possible, because if you have so many files, you don't want to go read all of them. What's the strategy to narrow down only the important files? And this is something you can do yourself. You can like find some custom way of thinking about it and follow. But we decided to use an open standard called the Delta Lake protocol. And Delta Lake is brilliant in its simplicity. It's just a lot of metadata files. For example, in a Delta Lake directory, we would have a Delta log directory that tracks like metadata, for example, which information is in which of these packet files, etc. So, and that gives us a lot of superpowers, you know. So we decided to build on top of Delta Lakes, and Timefusion basically brought all these building blocks together, such that when ingesting, we can go through Delta to write the packet files and then write some metadata and store both the packet files and the metadata to S3. Then when querying, the same thing, we go to Delta to find all the metadata of which packet files exist, what information is in which of them. Then we can query those files and pass them to datafusion, as well as the query and datafusion can give us an execution plan of, okay, based on the query, maybe you need to join here, you need to ignore these files, etc. Um, yeah, so we implemented all of this together, and we went a step further, which was implementing the Postgres wire protocol for our custom Timefusion database. We were able to use a library called datafusion Postgres. The funny thing is, at the time when we built this project, datafusion Postgres was a sort of POC example repo. It wasn't like something anyone should use to build anything. So we had to fork it, implement support for actual things that are needed in a database. For example, we implemented support for insert queries, update queries, authorization, just a lot of things actually. But the good thing is that there was some building block that we didn't have to start from zero, and eventually we were able to um, to push all of these contributions back to the original project, and now the project is more robust and also used by even other big companies at the moment. So yeah, we outside of implementing the data fusion, the Postgres wire protocol, we also realized that we had all of this code that was built to work with timescale DB. So since we are building this database ourselves, why don't we just borrow all of the amazing ideas from Timescale and just steal them into our project? So we ended up implementing a lot of the functions. For example, this code snippet I show here is an implementation of the time bucket function, which is an innovation that came from Timescale DB. But by adding it, implementing all of these custom functions and features into our new database, it meant that migrating from Timescale to our new database was as simple as just changing the connection string. So instead of querying Timescale, we simply queried Timefusion and no change in code. And the result was, yeah, a lot of actually amazing things. For example, um, just by building on top of object storage, we're able to just automatically support a bring your own bucket model, where customers could give us an S3 bucket and all of their data gets stored there, not hot and cold storage, but that their own buckets became their primary storage. And since we operate in the German market, and Germans are very obsessed with data privacy and GDPR and all of that stuff, it was like a no-brainer in this market. So yeah, a lot of things. I know there's not as much time, so I'm just gonna speed through some of this. Um, by doing all of this, we're able to separate storage and compute. Our storage costs became a fraction of what they were, even compared to when we self-hosted Timescale DB. And we no longer had to over-provision server storage because the storage was now in like S3 compatible buckets. In our case, we use Cloudflare R2, but we have users who use MinIO even. And we could scale our query runners, that's the servers that actually execute the queries, up and down with like 1 GB of storage, no problem, as long as they had all the CPU needed to execute the queries. So it turns out that don't build a database is mostly right. but sometimes you are forced to. And if you stand on the shoulders of giants like datafusion or Delta Lake, you might not just solve the original problem, but you might build like your biggest competitive advantage. Um, just as a quick one, I wanted to show like a quick demo of what this looks like. Sorry, excuse me. Um, yeah. So I just run some quick queries. So this is I have this running locally now. So let's just connect again with the PSQL. So now I can run like a query. And the funny thing is, all of these queries you could see how quickly they were. If I enable the Postgres timing, you'll see this executed in 66 milliseconds. Now the files that power this query all still come from this Cloudflare bucket here. And if you remember from my talk, you can see the Delta log folder, which tracks all of the metadata. And then you see a folder for each day. And if I open any of these folders, then what you see is a bunch of packets files, a bunch of packet files. And because of how optimized the query engine, the packet file format is, you can see it's just a bunch of kilobytes. I was showing recently that this project here stores something like 800K events per day. But then if I sum up all of the files created, it ends up being like under 10 megabytes per day, just because of how optimized the Parquet formats can be for this kind of data. Okay, I think I can stop here for now. I don't know if there's any more time or if there's any questions. Maybe the moderators can let me know. Okay, while I wait, there's a question. Does Monoscope support sampling out of the box? Yes, because it built on the OpenTelemetry library. So sampling is a feature of OpenTelemetry, not Monoscope. So we just receive the data and analyze it. Another question was, is all time series data stored in disk all the time, or nothing is stored, nothing stored in memory? So the question is, the data is stored in object storage. So MinIO, S3 buckets, anything, so not on disk. We do have a feature where we have some sort of how do I call it? A sort of cache, an NVMe cache. So because these query running nodes are still servers, they still have some storage. It's a no-brainer to store any packet files or metadata that gets queried, very regularly on that disk as a cache. But this is just a encrypted cache. It gets deleted, like it's like a least recently used cache LFU. So it's capped at, like, for example, 1 GB. So anything above 1 GB gets deleted. So, and it only exists to speed up queries. Okay, any other questions? Yeah. So yeah, in that case, if there's no other questions, I ran through a lot of things because I feel like time was running faster than it was, but you're an amazing audience.
Can you hear me?
Yes, please.
Hi. Okay, cool. Thank you so much for the presentation. So we actually have 5 minutes now for questions. And we do have some questions, so I can read them out to you.
Okay.
So from the Q&A tab, so someone said, this is brilliant. How do you handle indexing? What about consistency/delay between storage and compute?
That's a very, very good question. And the two questions are things that we're constantly fighting and figuring out. Um, Not because they are necessarily hard, but because when you add object storage to the equation, it becomes a little bit more complicated. So the first question is about indexing. At the moment, we don't do much indexing, and it's not as much of an issue. Why? Because of how columnar data works. So the packet file format is already optimized such that if you are running a query on any specific column, it's just super fast. And it's basically how a lot of indexes, for example, if you create an index in Postgres works, is they basically have like a basically like one columnar, mini columnar storage, They pick out one column and track it separately with an that points to the row. So it means that we don't like we can be pretty fast even without indexes. But there are certain sorts of queries that we still need indexes for example, full text search queries. And that's something we don't support at the moment. What customers can do is do regex based queries. But we've been working on full text search indexes regardless, building on top of a project called QuickWit, if you've heard of it in the Rust ecosystem. It's basically like Lucene, which is what powers Elasticsearch. So we're trying to use that for text index. Now the problem is that it's built to store and track indexes on disk. So we are having to we've basically forked it and are trying to rewrite the entire engine of the index just so that it can work with object store and track these distinct files. So object store has a limitation that any file you store to it is immutable. So you can't just like mutably update an existing file, which is how this project works. So we have to like rethink the algorithm, but this is not live yet. This still needs some time. The second question was about like latency. Um, it is a very big problem, and it's for most queries, it's actually not a problem if the query doesn't touch too many files on object store. But if you run a query that has to touch, for example, I showed here that we have like a different folder for each different day. So each of this is called a partition. So basically the data is partitioned by day. So if I have a file that has to go through many of these partitions and touch many of these packet files, then that is a lot more latency. Even if you're dealing with 20 milliseconds network latency to S3, if you multiply that by the number of files, you end up with like 200 milliseconds. Um, this is limited by the laws of physics, and we've not yet derived superpowers to break the laws of physics. But how we work around that is by tracking metadata. So if you read the code base for Timefusion, you see that a lot of code is spent on intelligent metadata handling. The metadata tells us what information, what range, for which columns, for which range is in which of the packet files, so that we can query only the exact packet files that has the information we're looking for. That way we don't have to touch many files and incur the latency of touching many files. The second thing we do is I mentioned this intelligent data caching, where packet files or metadata files that are used very often can be cached on disk, so that basically reducing how much calls we have to go to S3 for very important information. Did that answer the question?
Yeah, I think that was good. Thank you. So we have some more. And we actually have some time. So we have 6 minutes. I think I told you had 5 minutes before, but we actually have some time. So,
Okay. Maybe I can calm down a little bit.
Yes. Okay, cool. So one question was, I think you talked about performance a bit just now. So one question someone had was, what were the gains you had? So the person asked what about performance, but I think you've answered a bit about performance. And the second part was, what were the gains you got from like an ingestion and query perspective?
So in terms of ingestion and query, I don't think we got like any special benefits that we were not already getting when using Timescale DB. The main benefit we got from building this, ourselves in our own way, was more about having the data in object storage so that we don't have to get these 100 terabytes, 500 terabyte servers that end up getting full after a couple months. So, that was the big benefit. As for the querying or for the ingesting, we were able to implement an asynchronous ingestion engine. This is an idea I stole from the ClickHouse project. They actually released that feature, I think, early this year or late last year. And that was at the time when I was actively hacking on Timefusion. So I was like, so this is possible, and then I just implemented it. And what that means is that when you write in Postgres has to confirm that it has actually written the file to disk before the query completes. And that takes time. And for us, we are constantly writing new information. We are not like, it's telemetry data. It's not like a fintech platform where you need to be sure that the transaction has been written before another transaction runs. So we have some flexibility. So we simply, as when you write, it's instant. I didn't prepare an insert query, so I might have to check history to find one to show. But as you write, our engine would simply collect the information and tell you, yes, successful, but it hasn't yet written it to object store or written it anyway. It keeps it in memory for like a second and then slowly write. That way, we're able to just write a lot faster than with Timescale, just because we are not doing as much work as what Timescale is doing when we're writing. It also means that if the Timefusion database crashes before, after you do an insert, but we've not yet committed it, if the server crashes, then we might lose that information that was not committed. So it's a trade-off, but that is an okay trade-off for my industry. The other question was about performance. So I came here to show you what the response times look like. They vary. It can go from 66 milliseconds because some metadata was already cached or we only read one file to 500 milliseconds because we had to read so many metadata files and download so many packet files. It also varies based on my internet. So when I'm in Nigeria and I'm running this test project, then the latency becomes a little bit slower just because it's internet. But in the cloud, where it's all super fast gigabit internet, you can expect, I would say sub-second latency for most requests.
Cool, thank you.
Okay.
I think the answer is, so we can probably take two more questions. So someone said, I think you talked about this a bit just now. So someone said, is time series data stored in disk all the time, or do you store some in memory? And I think you just talked about that, right?
Yeah, so it's not in disk, but on object store, which eventually is in disk, but someone else's disk. And we cache some data both in memory. We have something called a hybrid cache. How that works is that when new information or information that is queried very often happens, if enabled, we cache some of it in memory. And then when we're hitting the limit of, for example, if the hybrid cache can only keep 10 gigabytes of data in memory and we're exceeding that, we can store the next gigabytes to disk. Different performance, but it's a trade-off here.
Yeah, makes sense. All right, real quick, someone's asking, is Timefusion open source?
It is open source, and please give us a star on GitHub. You can access it by going to github.com/monoscope-tech/timefusion. And I'll bring you to the project. So this is to give us some stars. We don't have a lot of stars. Yeah, while at it, also give the Monoscope project a star as well. So it's the same /Monoscope. Yeah, they're both open source. Timefusion is in Rust, but Monoscope is in Haskell. So don't be stingy with your stars.
Cool. Thank you. All right. Someone asked, are stop procedures enabled? Can you use stop procedures with Timefusion?
At the moment, no.
Okay.
We have to pick our battles. So that battle is not for right now.
Yeah. Someone asked, how do you deal with high cardinality data? So we have, we're going to end very soon. So just
Okay.
keep that in mind.
So high cardinality data is precisely the strength of Parquet. So it's not even, we don't even have to solve that problem because Parquet file format is built to solve exactly that problem, which is that, no matter how many, no matter the cardinality, each, for example, tag or column um, is kind of stored separately and it's handled on its own in some sense. I had a slide where I showed this. And so it's just no matter how many columns, for example, you can have 100,000 columns in Parquet. And it doesn't, if, for example, if you have 100,000 columns in Postgres, you might not be able to run the query because Postgres has a row size limits for when you're querying the data out. But Parquet does not care because as long as you're not querying all the columns, if you're querying like 1,000 of the columns, it's fine. It doesn't have to read the entire row. You can read just column by column.
Cool, nice. And I think final question we can take is how large is the team? I'm thinking of maintenance overhead of these custom tools whilst you're maintaining the core platform. How do you manage that?
We're a small team. We're under 8 people. I think in our Monoscope project we've had maybe like 11 maintainers on the open source project. So it's very small and it is a very, very valid challenge. And I think it's important to pick your battles when you're a small team. But in this case, what we what Timefusion became um, was only possible because we built it ourselves. For example, the bring your own buckets feature has become one of the key selling points of our platform because when customers come to talk to us, they say, why should we use you instead of, for example, Datadog? And then my first question to them is what is your data retention and data log? And a lot of the time it's 3 days because Datadog is too expensive, so they can only keep 3 days of logs. And then we tell them, hey, you can plug your own S3 buckets and you can have, I don't know, forever, 10 years and still query it. So that has become a business trend that was only possible because we built it. Since no off-the-shelf database lets you do implement a bring your own buckets feature. Yeah.
Yeah. All right, that's really cool. So I think that is all we can take. Thank you so much, Anthony, for your time. This was really